Hi everyone, I wanted to save you guys some time and go over one more lesson. This will be our final lesson, um, considering our situation and the number of classes we had. So I'm going to work on what we call the difference quotient, and this is a calculus related idea, and it's going to take what we've been working on with limits, and we're going to apply it to find something called slope. And slope is something that we've seen in straight lines. If you guys remember the equation y equals to mx plus b, the m was our slope, but this was specifically only for straight lines. The example, if I write y equals to 3 over 2x plus 1, the y-intercept was our b value here, which is 1, so we count 1. We count the slope m, rise up 1, 2, 3, run 2, and that was the slope of the graph, which is straight line. And one thing that we realized that if I go up 1, 2, 3 again and over 2, or down, back 1, 2, 3, and back 2, these are also points on the line. This is how much the line grows. And it's constant. The slope is never changing for a straight line. It is always going to be exactly the same. In essence, it tells you how fast the line is growing, right? If you look at this idea as b is my starting value, and as x changes, it's growing at a rate of 3 over 2. So if I have a positive growth rate, the line would be increasing. But if I had a negative, y is equal to negative 3 over 2x plus 1, only thing changing is the slope, we would go down 1, 2, 3, and down to the right 2. And that would give us a negative slope. And again, the growth is constant, 1, 2, 3, 1, 2, 3, and over 2, constant, 1, 2, 1, 2, 3 over 2. It's the same growth rate. Now, our big deal is that most things in the world are not graphed by straight lines. So our dilemma was, how do we still say how much something is growing, though it's not going to always be constant? And if I give you guys a simple graph, and let's use example, y equals to x squared, and we know this is pretty easy, and we know this is not a straight line. This is a what? Right? A U graph. To make that a little nicer. This is a quadratic, so it gives us a parabola. So if I plug in some numbers, if x is 1, 1 squared is 1. If x is 2, 2 squared is 4. If x is 3, 3 squared is 9. Well, that's way too big. And 0 is 0. And we graph our parabola here, shooting it to the stars. And on my left side, the same thing. If I put negative 1, it'll be 1. And negative 2 would be 2 squared is positive 4. We end up with our little parabola here. Now, to describe what is the slope of this graph here, it's going to be a lot more difficult because the slope is not going to always be the same. Now, I'm going to use a little ruler here just to demonstrate that. A slope is how much the line is changing. So if I look at over here, the slope is constantly growing at a constant rate, up 3 over 2, up 3 over 2, up 3 over 2. And it's going to be the same rate for this whole graph. But if you look on the parabola, at every point that I choose, it changes the slope of the graph. As x changes, y changes, and so does the slope. And as you can tell, as x gets larger, as x gets larger, the y changes and it grows even faster. So my slope gets larger as x gets larger. So when x is 0, our slope is not changing. And as x becomes 1, it's more positive. X is 2, more positive, and the growth increases. And we end up with a problem of there is no one slope. The slope is constantly changing. So how can I find out what the slope is? Is there an equation I can use, just like in slope-intercept form? On the left side here, just to take a notice, that the slope here would be negative. I'm actually losing value. The values are decreasing. Okay, so back in Algebra 1, we had a cool way of finding slope. Well, not cool, but it was easy. And we could look at their formula. But if we didn't have the formula, we could always find slope using this equation. M equals to y2 minus y1 over x2 minus x1. And that was our slope equation, where we take y values, because isn't y our rise? And x is our run. So we take our rise over our run, which is another way to describe slope, how something changes. Now I'm going to pick up 2 points here. We said this was rise up 3 and over 2. So that's going to be a 2. 3 plus 1 is 4. So this point here is 2 comma 4. And this value here is 0 comma 1. These are the points of this line. And if I use my slope equation on my right here, m is equal to rise y2, 4 minus y1, 1 over 2 minus 0. We end up with the same slope, 3 over 2. Now, you could do this for any of the points on this line. If I look on my left here, this value here was going to be a negative 2, comma, negative 2, I think. Negative 2, negative 2. And if I plug this into my equation, m is equal to negative 2 minus 1 over negative 2 minus 0. We end up with negative 3 over negative 2, which is still 3 over 2, the same points on the same slope. And since this is a straight line, remember how it's never changing? I can also use my first and third point here, my first and third point. M is equal to 4 minus negative 2 over 2 minus negative 2. And this doesn't look like it would be 3 over 2, but it turns out to be 6 over 4, which reduces to 3 over 2. Now, if I try this with my parabola here on my left, points 1, 1, point is 2 comma 4. Here is going to be 0 comma 0. If I pick 2 points, would it give me the same slope throughout the whole graph? So let's pick these 2 points right here. I'll take those 2 points, and let's see what slope that gives me. 1, m is equal to 1 minus 1 over 0 comma 0. Oh, sorry, my mistake. Y minus y, y minus 1 minus 0, and 1 minus 0, which gives me a slope of 1. And that, for the most part, that is kind of true. We do have an overall average rate of change, that's another keyword, average rate of change of 1. But this slope here isn't representative of all the slopes in between. And this slope is actually just an overall average change, because at every point in between, the slope is actually changing as I'm on this graph. It is constantly changing. So we can't actually use this formula as it is. So what we say instead in calculus is, if you want to find the slope of one specific point, now let's try that again, y is equal to x squared, you have to tell me where do you want the slope to be found, because at every point it's going to change, right? Imagine if your mom says, where are you going to be today? Is it true you're going to be at the same spot the whole day? No, it all depends on what time. So let's say x is equal to 1. So at x equals to 1, what would the slope look like? So in our parabola here, when x equals to 1, what would this slope, the slope of a tangent line is a great way to look at this. A tangent line hits the graph exactly at one point, and that also represents the slope of the graph. Why is there only one tangent line? Let me demonstrate that to you in a slightly larger picture. Oops. If I give you a point here, let's take that as my point. I want to find the tangent line, the slope too. Why is there only one tangent line that goes there? Well, let me go ahead and draw you something kind of cool. A tangent line touches the graph exactly at one point. As you can see here, it touches it at exactly one point. And there's only one line that can do this, because if the line is a little too bent up, it now touches the graph at 2 points. If it's a little too flat, it touches the graph again at 2 points. See that? And that's not what we want. So the tangent line for us, it touches the graph exactly at 1 point. Let me switch the color there. Touches the line exactly at 1 point, and that's our tangent line. Oops. Let's make this a little better. The graph touches it exactly at 1 point. If it was too steep, 2 points, too flat, 2 points, it's always going to be exactly at 1 point. So let's try to figure out what the value would be for a tangent line. Our tangent line right here. What would the slope of this tangent line be? And again, we're talking about rise over run, but specifically to that one specific line, which is called the tangent line, and it also tells us how fast this graph is moving at that one specific point. So in calculus, we have something called the difference quotient, and that is done using this way. It's the limit. Let me write that actually. The difference quotient. And that's made of two words that we know: difference for subtraction, and quotient meaning division. So difference quotient is the limit as h approaches 0 of y2. Oh no, let's write it a different way. Let's do f of x plus h minus f of x over h. And that might seem kind of funny, but that's defined what h is. H is the distance between the 2 points we're going to use to find the slope of a line. Now, to find slope, like we mentioned before, in order to find slope, we use the equation y2 minus y1 over x2 minus x1. So if I just pick two random points, we have a y2 and an x2 and a y1 and an x1. So to find the slope of this line here, we would subtract the y's from the x's. We would subtract the y's from the x's. Now to simplify this, mathematicians said instead of saying x minus x, isn't x minus x just some difference by how far they are in one direction? So they just said h is really x minus x. How far do you want the first point to be from your second point? Okay, how far do you want the first point to be from your second point? So for this part here, the h is really x2 minus x1. It's really our x values. Well, how do x's and y's, how are they affected? Well, if x changes, doesn't my y change? So here's how they rewrote this. Instead of just calling it y, let's call this a function. Let's say we started the problem here. I'm going to write this a little bigger now. We're going to say this is x and f of x, which isn't that another way of saying y? This is my function, f of x. Well, if we represent it this way then the point on the right, instead of saying x and y, the point on the right is x plus h, because I took your x value and I added h to it to become x plus h. If you were at -1 and I said, hey, add 3 to it, we are now at +2, our right point. So our x value, x plus h, and our y value now is, instead of plugging x, we call it x plus h. Why? Because the y value is always going to change based on the x value you plug in. So over here, the y value is when I plug in the x, and when I bump it over, see this point number 2 is the bumped over version. What would the y value look like? Well, plug in the new x plus h value there. In this case, if my original value was -1, that's where we started, and we went to 2, right? Because we went 3 spaces over. My h is 3. Well, the f of -1, that's my first starting point, and f of -1 plus 3 is f at 2, my new y value. So taking that idea here, let's go back to the slope equation. The slope equation says y minus y. y minus y. Well, it's y minus y. I'm going to write that down a little bit lower here. It's f of x plus h minus f of x. That is my y minus y. Over, slope says x minus x. X plus h minus your original x. We can simplify that a little bit. F of x plus h minus f of x. Look down here. What subtracts out? The x's, and we're left with just h. And this is our difference quotient here. It's really the same equation of saying y2 minus y1, but instead of writing a bunch of y's, we're just going to use the same f and the same x, and only thing changes now are h. You just tell me how far apart the points are. So our whole idea of difference quotient, how to find slope, is using our algebra 1 equation for slope, just rewriting it a slightly different way. Instead of using x and y, we're just going to use f, x, and h. And h just tells me how far the 2 points are away from each other. Let's use another example here. If I give you 2 points, color, and the point is 3, 2, and we'll take a point right here, 1, 1. Okay, 1, 1. What is the h value between these 2 points? Well, if this is 1 and this is 3, how far are the points away from each other? Well, it's just 3 minus 1 is 2. That's how far the points are away from each other. And that's our run. Going back to the difference quotient, the way we use it to find slope is that look how far what value do I want for the h? And if you go back here and look, I'll make this arrow a little easier to read. Remember, h here is really our x value. And how far do I want this little bump, this little difference? I want that to be pretty much 0. Looking at a picture, what we talked about before, of a parabola. If I told you this was my starting x value, which is 1, I want you to pick a different point to find the slope. If I pick a point that's too far away, this line is not representative of a tangent line, too far away. If I pick a point that's closer, this one, oops. This one is a little bit better, but not really it, because really I'm looking for a point like right here. So as I get closer, my 2 points get closer, my tangent line becomes more representative of the true slope. So we're getting closer, closer, closer. Once we're here, we have our tangent line. So here is what we want to do. We want to go ahead and find the slope using 2 points, but we want those 2 points not to be so far apart from each other to get a really bad value that wouldn't be accurate of the tangent line, but one that's very close. So we make h so close that it's practically 0. Now, we could just plug in 0. If I just plug in 0 here, is it okay to divide by 0? And the answer is no, we can't divide by 0. So that's what limits allow us to do. It says, hey, what would it look like if those points were so close together that they were not far apart at all? They were on top of each other, which is impossible. You can't find a slope with just 1 point. You need 2 points. But the limits say, what if they were so close together that there was zero space between those 2 points? So let's go ahead and demonstrate what happens here. The limit as as h approaches 0 of f of x plus h minus f of x all over h applied to this function x squared f of x at x equals to 1. And that was our initial question. What was our slope going to be? What's our slope going to be, right? We started right here. What was our slope going to be at x equals to 1? So here's what we do. We start off with the problem, the limit h approaches 0. You have to find out what your f of x problem is. Well, f of x here is just x plus x squared. So we're going to fill this out. H doesn't change. We know f of x on the right, that's going to be x squared, because I got it from that's my function. What's my f of x plus h? It's just x squared, but instead of writing x, you have to write x plus h. X becomes x plus h. Side example, what if I told you f of x equal to 3x plus 2? Okay, well, the limit formula would be limit h goes to 0, h on the bottom, it's going to be f of x plus h minus f of x. Well, hey, don't we know what f of x is already? That's 3x plus 2 on the back. Does not change. And the front gets the upgraded version. It gets the x plus h version. Take a moment and look at what I did here. The front equation and the back equation are exactly the same, except whenever I have a variable x, I have to plug in the new version, the x plus h version. X plus h version. Let's do this one more time. If f of x was sine of x, the limit as h approaches 0 of, again, f of x plus h minus f of x, we're going to write h on the bottom doesn't change. On the back side, f of x doesn't change, that's just sine of x. But the front, remember how we have x plus h? That's going to be sine of x plus h. So we want to practice being able to plug that in a couple of times. I want you guys to go ahead and try this. What if f of x was x squared plus 3x? What would my difference quotient be for this guy? Okay, go ahead and pause the video, or you can do it mentally, but pause the video and see if you can fill it out in your brain. What would that look like if you could plug this into the difference quotient? Okay, hopefully you were able to do that. Well, this is our f of x in the back. We're just going to copy exactly x squared minus 3x. If you notice, I keep writing a parentheses if I need to, if it's more than one term, because I want to make sure I don't forget to distribute that negative sign. And the front, every time I see an x, I have to write x plus h squared, because that's my x squared, plus 3 times x, which is now my new upgraded x plus h version, all over h. So let's go back. And why is this? Go back to see what we've been working on before. So let's finish up this problem. My semester code, this is a lot of work. Well, what's the whole point about this? Well, let's go ahead and ask ourselves a question. For limits, our goal for limits, we said before, is just to plug it in and see what happens. And we said h is 0 here. If I plug in 0 and 0, let's look at what nastiness is going to happen. This is x plus 0 is just x squared minus x squared over 0, which is 0 over 0. Do we like 0 over 0? Nope, we have a term for that. Starts with an I. Indeterminate. So we know there we have to find another way. So here's our other way. Go ahead and multiply that out. X squared, x plus h squared multiplies out to be x squared plus 2xh plus h squared. Hopefully you guys are able to multiply that out quickly now. All over h. We still have to write the limit because we haven't plugged it in yet. Look at the top for me. Do you notice anything? Sorry. Well, let me do that. Look at the top here for me. Do you guys notice anything that will cancel out? Is there anything there that would cancel out? I see the x squares. So we're going to be rewriting this. X squared minus x squared cancel out. So we're left with 2xh plus h squared over h. And if you can see here, there is a common h value that we can divide out. So we're going to divide out h, and h. That's going to give us limit as h approaches 0 of 2x plus h, because we had an h squared there. After we simplify the limit, just like finding the whole, we then try again. We're left with 2x plus 0. We don't have to write the 0 if you don't want to. 2x. The slope here turned out to be not one single value like we started off with. It turns out to be an equation that will change right along with x. It turns out that this is our slope equation now. And as we mentioned before, that as x changed for this parabola here, as x changed, so did all our slopes. As x changed, so did all our slopes. When x was 1, when x was 1.5, when x was 1.7, and as x became larger, so did all the slopes. And it's almost like we're predicting the future. We can figure out what that slope is. Now, we said we wanted to find out what the slope at 1 is when x is 1. Let's go ahead and plug in this. So my slope equation, we can, in calculus, we call this f prime. The derivative of x is 2x. That's an interesting notation. This is f prime, f prime. Now, what value do we want to check? We want to check f prime at 1, the slope at 1, which is just 2 times 1. It turns out our slope is just 2. Now, I want to make sure you see that this is actually that this totally works. If I draw the parabola again, going to the left. Okay. If I ask you to find out what the slope at 1 is, we said it's going to be 2. So if I follow the curve, rise 1, 2 over 1. That looks like it could be 2. What does the slope look like at 2? Sorry, whoops. Well, if x is 2, x equals to 2, f prime of 2 is 2 times, well, x is now, right? X is now 2. It's 4. If I draw a line of 4, tangent line, 1, 2, 3, 4, over 1, that looks kind of it. What is the slope at 0? What is f prime at 0? 2 times 0 is 0. Look at the slope at 0. That is a horizontal line. That is the slope of 0. Totally predicted that one. What is the slope at -1? X is -1. F of -1 is equal to 2 times -1, which is -2. Take a look here. This is a negative slope, -2 over 1. So using the tool of the difference quotient, we can find the slope of not just one point, but of all points on a function that doesn't have a constant slope, like x squared. Or it could be sine, it could be x cubed, it could be a square root. All these problems can be done using this idea of a difference quotient. On Monday, when I see you guys, and Tuesday, I'll talk about the other different types of equations that we'll be looking at. We'll see square roots and we'll see fractions. And these are the other types of problems that we'll be having to work with to find the difference quotient to